In this video, we're going to discuss calculation using bases. In the pH system, our pH is equal to the negative log of the H plus concentration. Well, in water, remember that our water is in equilibrium with breaking apart into H plus and OH minus. There's always hydroxide around. Truth be told, we could have watched the hydroxide. There's no reason we had to watch the H plus. Our focus could have been on the anion. By convention, the H plus is what we use to focus on, but there is an equivalent process going on for the hydroxide the entire time. We can talk about the log of the hydroxide concentration. So the POH is the negative log of OH minus. Well, because water Kw is equal to the H plus times the OH minus concentration, as one changes, it alters the other. These two will react until they reach equilibrium to always equal our Kw, which at 25 degrees is 10 to the minus 14. So if you know one of these concentrations, you can always solve the other concentration. A couple of equations for this. We can also solve that the pKw is equal to the pH plus the POH. pKw is, well, 10 to the minus 14, take negative log, 14. So in water, pKw is going to be 14 at room temp. 14 will equal the pH plus the POH. So if you know the amount of hydroxide in solution, you can still solve the pH. This is particularly useful if you were to make a 0.0015 molar sodium hydroxide solution. If we have a solution with excess hydroxide added, we still might want to know the pH of it. Granted, it's most easy to calculate the hydroxide concentration, but we can always relate that to the amount of H+. And by convention, we always care about the pH. That's what all the data is correlated for, all the safety notices are written for. Despite knowing the POH is equivalent, it's the pH that everything is written for. And so we'd have to convert our concentration of hydroxide to find that pH. Well, the POH is negative log 0.0015 molar hydroxide. That will give us a POH of 2.834. So if we want to solve the pH, 14 equals the pH plus 2.834. So we subtract that from both sides, and we will find 11.176 is equal to our pH. That's much greater than 7. It's pretty basic, which makes sense. We added a fair amount of a strong base, sodium hydroxide. In situations where you're looking at a solution that contains a base, solving the POH and using that to find the pH is the simplest means by which to identify the H plus concentration. Well, for a strong acid and base, that's fairly straightforward. What about a weak base? For a weak acid, we had to do an equilibrium calculation using the acid breaking apart into base. But if we put pure weak base into solution, say ammonia, well, normally we think of the weak acid, we say NH4 plus breaks apart into H plus, and its conjugate base, the ammonia. Unfortunately, this is for when we have the acid breaking apart and making the base. That only works when using acid. If we're using the base, our base is going to react, but it's being added to water. There's not a lot of H plus around, some from water, a little bit in there, but mostly there's a lot of water. And the reality is it's going to run into a water far more often. Well, water is amphoteric. It can both accept and give away a proton. And so you can make in this case NH4+, and a hydroxide. When our ammonia base interacts with water, it can take a proton from the water, making ammonium and hydroxide. This would be the equation using our base acting as a base. So in situations where we're talking about pure weak base, we need to convert our equation. We can't simply look at our normal weak acid expression. We have to think about what the weak base is doing on its own. Nonetheless, the calculation is fairly similar. We find some initial concentration, some change, and some equilibrium concentration. Our base, we're going to start with some base. Let's do 0.025 molar ammonia. So initially we'd have 0.025 molar ammonia. We'll assume it's 1 liter. Make our calculation simple. Our moles will equal our molarity. So we have this many moles of ammonia. The concentration of water effectively doesn't change. It's 55.5 molar. It's not going to be significantly altered by these reactions. Our initial ammonium is none, and our initial hydroxide from this reaction is none. There's going to be some change. Well, the only thing I can do is act as a base. So I'm going to lose some of my base. Nothing's going to happen to water. Technically a little will break down, but it won't really alter the concentration of water. I'm going to make some of my conjugate acid, and I'm going to make some hydroxide. Eventually we reach equilibrium, where our starting value minus x, and x will be our concentrations. If we wanted to find this equilibrium, well, our products are the conjugate acid, the hydroxide, all over the conjugate base. So our equation is reversed a little bit. Water is constant and factors out. This is not Ka. It's equal to some constant, but in this case, it's a K of a base. It's a Kb. We need a Kb value. Some of these can be looked up, but we can also calculate it from the Ka value. For a conjugate acid-base pair, if you know the Ka, the Ka times the Kb must equal Kw. Since they're participating in the equilibrium with water, it works out that the conjugate acid acting as an acid, its constant, times the constant for the conjugate base acting as a base, that product must equal the Kw. For ammonia and ammonium, well, ammonium's Ka is 5.6 times 10 to the minus 10. So we can solve what the Kb for the conjugate base of ammonium is. So for what our ammonia is, which is what we need for the reaction we are performing. 5.6 times 10 to the minus 10 times Kb equals 10 to the minus 14. Our Kb then is 10 to the minus 14 divided by 5.6 times 10 to the minus 10. We'll find that the Kb is 1.786 times 10 to the minus 5. We can plug that in to the expression for our equilibrium reaction. And so 1.786 times 10 to the minus 5 must equal the ammonium, the hydroxide, over the ammonia. So we found the constant for equilibrium. We found that equilibrium K value for ammonia acting as a base. We had to find it from its conjugate acid, but we were able to do that through the relation that the Ka of a conjugate acid times the Kb of its conjugate base must be equal to Kw. Plug in our equilibrium values. Well, that's going to be X molar ammonium. That's going to be X molar hydroxide. And we can probably assume X is pretty tiny for our ammonia. Let's make that assumption in this case, in which case 0.025 is going to be the concentration for our ammonia. Rearrange and solve for X. What we'll find is the X is equal to 0.000668, which means the concentration of our hydroxide is 6.68 times 10 to the minus 4. We can take the negative log of that to find the pOH. We'll find that is 3.175 is our pOH. Well, we're always trying to reference the pH in the end. That's the convention. So if we know the pOH, the last step is to find the pH. The pH will be 14 minus the pOH. So 14 minus 3.175. The pH is 10.83. What is the pH of a pure weak base? Well, it's similar in how we calculate it to the pure weak acid. However, we have to set up our equation slightly differently. Our base acting as a base when it's pure in water means the base has to react with water. It'll make conjugate acid and hydroxide. We can solve that hydroxide concentration using our equilibrium expressions. Once we have the hydroxide concentration, we can solve the pOH and use that to find the pH.